Yeah, but just partially. Thank you for the introduction, and thank you all for having me here today. My research, is about additive manufacturing and construction. I'm working in a collaborative research project at the Leibniz University Hannover. Together with my colleagues Robin and one of our students, Lars Dittrich, we performed the experiments I will show you today. But first, let me give you a short introduction to our process. So we're dealing with shotcrete 3D printing, as you can see here in this video. And shotcrete 3D printing has some benefits like improved interlayer bond strengths and the ability for reinforcement integration. However, there are some major flaws when dealing with this process. One of it is that shotcrete 3D printing initially is an unstable process. So when we make a small error in predicting the layer height that we want to produce, like during the planning phase, this error will result in a, for example, wider but smaller layer height. Or if we overestimate the layer, it will be vice versa. And these errors will stack up during the production process. Like you can see on the right side, the layer is getting wider and wider over time, leading to finally a print failure. This is why we came up with an online feedback control system. This is just the rendering of it. We attached a 2D laser scanner to our printing system. We're measuring layer width and layer height. And we then developed some controllers, which are currently controlling like the feed rate, the spray distance, the concrete volume flow. And within the first experiment, we were quite happy that we can show how the system is able to compensate for underfill, for overfill, or even for integrating objects. The issue is when we are transferring this knowledge to larger building components. So these are small scale experiments, and we are currently trying to print like like larger object up to 2.20 meters in height. We need an excessive amount of reinforcement to build structural components. And this reinforcement can in the end be seen in our data sets. So what we see here is 3 lines recorded with a 2D laser, and we have those hills in there. But we cannot distinguish, is this concrete, which we want to control, like overfill or underfill, or is this some sort of reinforcement, which is not affecting our material application? So this was the point where we said, okay, we need some additional information to distinguish between concrete and integrated objects or reinforcement to stabilize our controllers. And therefore, we thought about workflow. So we would try to use depth and color images to distinguish between concrete and reinforcement. We then would try to identify the rebars and reinforcement within the color images, transfer this identified pixels to the depth image. Then we get the depth data where we have reinforcement in our component, and then we can transfer this to the robot workspace and distinguish between concrete and reinforcement for our controllers. So the first thing we did was we extended our process control unit. We attached a real sense camera, the Wi-Fi, also battery, power supply, everything that we needed to evaluate the image data. And we applied this to our test bench in Hanover. The videos were taken at the TU Braunschweig that you've seen before. However, I have a small test bench where we used PU foam instead of concrete. It's easier to handle for me alone. And we started taking the first pictures. You can see on the right side of this that we painted the PU foam in black color to reduce the color contrast. Otherwise, we thought about, okay, the neural network will only train the contrast and thereby identify 3 rebar. However, this will never be the place or the same situation when applying the network to concrete. So we then recognized that there's a significant difference between images that we record during static operation of the robot, like driving somewhere, taking an image, or during a motion. You can see on the right side that when the printer is moving, we have a significant portion of motion blur. So we needed 50-50 for our training data sets for the network. So it's about more or less 1,000 images that we recorded. Thanks to my student, they're all labeled. Yeah, 50-50 motion blurred and clean images. We then initially thought about using some analytical image processing to evaluate the data sets, because usually these approaches could be much faster than using convolutional neural networks. However, applying things like canny edge detection, thresholding, this didn't work out quite well, leading to our conclusion that we probably just train a neural network to identify the rebar within these images. We straightforward used YOLO V8. We have the pre-labeled images, 150 training cycles, and we can see on the top and bottom here on the images that the trained network is more or less able to identify the rebars. Accuracy is about 66%, which for us is more than enough, but I'll come to that later on. So next step was we now have the identification done. However, we need the segmentation too, because we just want the depth pixels later on, which belong to exactly the inserted rebars. We therefore, again, just went straight forward with YOLO, trained it. It's more or less 100% of accuracy for segmentation. We then need to align the color in the depth image. Without a proper alignment, you will end up detecting rebar where there's none. In reality, you can see it in the top part of this picture. There's a quite significant difference between both images. However, after alignment, we conducted our first inline measurement experience. So again, we printed one of the foam columns, we painted it black, we inserted the rebar, and then we used our system like the Dörrie robot attached with the measurement unit and moved one circle on the top. We fulfilled one circle. Processing frequency is about 1 Hertz for getting the image, running it through the convolutional neural networks, and getting out in the end the depth pixels that we want to have. The feed rate of our printer currently is about 100 millimeters per second, which leads to having more or less the same rebar or the same reinforcement element in more like 3 to 4 pictures. This is why the accuracy of the image processing with 66% is more than enough. So we have 3 images showing the same reinforcement element. 2 times we can detect it, but it's enough if we detect it once. So what you can see here on the top is again the printed foam column. On the right-hand side, a more detailed image of the top. On the lower left, you can see the stitched or transferred depth image of the camera, all of it. And on the right-hand side, the image that is provided by our algorithmic approach. And you can see here that we have in green every point that's assigned with the label concrete, and in red everything that's assigned with the label reinforcement. And as I already mentioned, the accuracy is about 66%. So we have green dots in here, which are labeled as concrete, but which belong to the reinforcement. However, we, for each of the reinforcement bars, have at least a small amount of points labeled as reinforcement, which allows us to detect each of the inserted short rebar elements. Currently, the accuracy, the depth and XY accuracy is about 4 to 5 millimeter. This is due to the cheap camera that we used, and the transformation from camera to the robot workspace currently is just, let's say, in CAD-based guess. Could be improved in the future. However, this is more than enough that we need to stabilize our control approaches, which initially were the main reason for us to deal with this topic. So we then used the same network, the same sensing unit, just mounted it to the production facility that I showed in the first place in the videos. We again recorded the images during printing. And what we can see here on the bottom right is that, again, the accuracy of detection and predicting detecting the reinforcement is again about 66%. So it's just the same neural network. It's the same data sets for training, just applied to a different process. What you can see in blue is the 2D laser line, just for curiosity. So coming to a short summary and conclusion, we used about 1,000 labeled data sets for training. The detection accuracy is about 66%. We proposed a workflow to get from the acquired depth and camera images to the depth pixels, transfer them into the workspace to later on have more or less like 2 point clouds. One is concrete point cloud, the other one is the reinforcement point cloud. For us, in this case, it's important for the controller. However, we came to the conclusion that this enables us to also identify and localize reinforcement within the printed component. So from now on, when we are printing structural component at the TU Braunschweig, we usually in the end have 2 data sets. One is the data set for the concrete and one for reinforcement. And this allows us, for example, to evaluate the amount of concrete cover at certain positions within the reinforcement. Or we could also evaluate the accuracy of the applied reinforcement, like is it where we want it to be? which aside from stabilizing the controller, I think, or we think, was the real benefit of it. That's it for now. Thank you, everybody.
Okay. Well,
open for questions.
Yeah, thank you very much, Lukas. Thank you. Super fast. Do we have any questions for Lukas? Yes, there's one in the back over there.
Thank you, Lukas. Very interesting presentation. This is Jianzhong Zhang from Purdue University. So you have talked about a lot of the accuracies around 66%. But how about the other side? Is there any false alarms? Like, did you detect anything that should not be detected? And if so, what's the impact?
Yeah, we usually have detected like about 10% of false alarms. More or less, these correlate to stuff that's shown in the background of the images. So we don't have false alarms within the concrete, but some of the surroundings, which we based on where the object is printed and the CAD model, which we can just easily exclude because they are like 2 meters apart from the object that we're printing. Yeah, but they are there, definitely. Yeah.
Got it. All right. Thank you.
Thank you. Yes, there's a question there as well.
Well, thank you for your presentation. Let me ask the question from a different perspective, thinking about what your algorithm can do compared to a set of bare eyes that people in the field can do. I think one interesting observation I have is, let's say your algorithm has over 60% accuracy in detecting the existence of all these rebars. I can look at the picture and I can tell how many rebars we have within a second as well. So what is the practical value of this type of research when you implement?
The thing is that, just let me step back to the slide. We stopped the printing process at this level. However, usually we would continue printing. So, for example, if we add these rebars down here, and then we continue printing, you won't be able to tell anything about the reinforcement in the object anymore. And since this is running during the printing process, so the evaluation algorithm and the proposed algorithm is working during printing. So in the end, you won't see any of the reinforcement anymore, but you will know by the data sets that it's in there and how much is in there and where is it. And yeah, that's the benefit. However, when I show you an image here of the final product, you won't be able to see anything. That's why I stopped at this point. Thank you.
Yes, David. Oh, hold on. There's a microphone coming down. Yeah, but there are people online as well.
Again, thank you for a great presentation. I guess my question is less about the algorithm and the accuracy of the algorithm, and more, when this works, what is your primary application? Is this about certifying things and about permitting, or is it about other things?
So for me personally and my PhD thesis, it's more about the part in the beginning. Oh, working. Oh, come on.
Try keyboard.
Okay, skip one. Like this one. We have those control algorithms, and they work based on evaluating the distance from the scanner to the concrete. And as soon as we insert like short rebars, these data gets corrupted. So I need to exclude the rebar from these control algorithms. However, this can't be done based on the laser scanner data because I can't differentiate between what is concrete and what's rebar or reinforcement. So I use this system and this algorithm to get the information, what I'm sensing currently with the laser scanner. Is it reinforcement or is it concrete? So to stabilize these control algorithms, that's my use case currently. Yeah, like, so yeah, this is the vision of the larger component, and you see the amount of rebar that's in there. this will definitely corrupt the control algorithms. So that's why I need those differentiation.
Okay, I think there's just us between you and your lunch, and I have 3 questions. So thank you very much again, Lukas, for the presentation, and everybody for
Thanks.
attendance.